much. Okay, right. So again, thank you very much for the invitation and for giving this opportunity. So I will continue with various applications of quasi-determinants, and I will start with orthogonal, non-commutative orthogonal polynomials. Okay, so let me recall that usually when in the classical mathematics, if you have just a function on real numbers, it's a sort of a measure, and then the integral over this measure by any polynomial is defined. Is finite, then you can define the actually inner product of pairs of polynomials given just by this integral. Now, if you have just complex functions, then you put actually bar over gt. But anyway, that's a standard way. And then you have a sequence of orthogonal polynomials, which defines by the following relations. So the degree of P sub n is n, and the inner product between pair of polynomials with different degrees is 0. Well, so that's very classical. But now, and you may construct these polynomials in a different way, but just one of the construction is based on determinants of matrices of so-called moments when you just integrate powers t to the n over this measure. And then you consider just a Hankel matrix defined by this polynomial, by these moments, and there is a way to define orthogonal polynomial. Okay, and so now I will do this in the non-commutative case, non-commutative generalization. So suppose I have just elements, any elements of a ring R. And so I defined now my polynomials just by using these formulas for quasi-determinants. So I have of moments, and in the right column, I have powers of t1, t, and so on, tn, and I start with the tn. And then by this construction that I discussed before, you have just a polynomial depending on t, and it's actually monic polynomial because the coefficient for t to the n is 1. So those elements, t sub I, they play a role of abstract non-commutative moments, and but from the construction it follows that those polynomials are polynomials of degree n. And let me explain in what sense they are orthogonal. Suppose I have an anti-involution of on my ring R. So which this is R, and then this R bar. And this is the involution such that the involution of C of moments are moments by itself. Then you can define the scalar product on the ring of polynomials. So R depending on T. It is central here. And this, so if you have for A T sub I pairing with BT sub j, then you put A, then you put this moment with the index I plus j, and then you multiply by B bar. Now, from properties of the quasi-determinants, it's easy to see that the product of P sub of the nth polynomial with the power of t to the I, if this power is less than n, is 0. And then you have, from this it follows that the inner product of two polynomials of different degrees is 0. So they are orthogonal. Okay, now in the classical mathematics, we know that orthogonal polynomials satisfy some recurrence relations. So you have just a connection for polynomials of degree n plus 1, n, and n minus 1. Okay, and now here with some coefficients, and here you can also define coefficients. They depend on Hankel matrices defined by those moments. So you have in the first row C naught, Cn, then the next row starts with C1, C2, and so on, Cn plus 1, and so on. And then you can define this quasi-determinants of this matrix of H sub k. This is southeast, means that you start with the element in the right upper corner. And this is for this matrix. And P sub k is quasi-determinants of another. So just k by k matrix. And then the coefficients are defined by this formula that you can see. And then you have this recurrence relation. So let me repeat again that if you specialize, if your moments are commutative, then you have exactly classical orthogonal polynomials and classical recurrence relations. So nothing is new here. Okay, you can actually develop these theories, consider different moments and so on, but right now I will stop on this subject and move to another application. And since this is a conference on integrable system, then I will consider the problem of iterated Darboux transformations. Again, let me give just an abstract definition of the Darboux transformation. So suppose R is an algebra with the derivation, and suppose that phi is an invertible element in this ring. Okay, so now we already use this notation, then the derivative of G is denoted by G prime. Kth derivative of G is just denoted by G, and this is to the power of K in brackets, also standard notation. Okay, then we define Darboux transformations of F by the following formula. This is like usually done in classical case. So this is F prime minus phi prime, phi inverse F. But according to our theory, this is just a quasi-determinant of 2 by 2 matrix. So this is basically some sort of a Vronsky quasi-determinant. We can define inductively iterated Darboux transformation just by the formula that's written here. So suppose you know what are your Darboux transformation for k-1 function, then the result you apply to just another, and here you have another function. So you apply this to this function, and you have this Darboux transformation. Okay, but it's easier to describe this, and this is, of course, just a theorem, that basically what you have just the Vronsky matrix, and you have this quasi-determinant. So, by the way, this column with f and its derivative, you can actually move it to the right. The result will be the same. So just start with the case derivative of f. And it correlates with with the classical definition, because this this quasi-determinant Darboux transformation in the commutative case is just the ratio of two Vronsky determinants, as it is. Okay, so just this one. Now let me just mention just briefly non-commutative total lattice, because I believe that Irina Bobrova talked about non-commutative total lattices. Vladimir Rubtsov will talk about non-commutative total lattices. But this is actually the first example that appeared in our paper, just in the first of our papers with Gelfand. And it was the following. So suppose you have just an element phi, which you call function or whatever. Then you consider this the Vronsky matrix, which are defined by derivatives of phi. And you take this quasi-determinant of this maximal, of the derivative of the maximal order of phi. And this element are satisfied the following system of equations, which is written here. And as you see in the left hand side, just in the commutative case, this is just a double logarithmic derivative. Now, in the non-commutative case, you have to be more careful, but so this is you write this like this. And so this is just an example of this. This actually historically our first example of a non-commutative integrable system. And you can investigate this, but I would like to have more applications. Now, the next, I will try to discuss again another relation between quasi-determinants as determinants, and this compared to what I did in the second lecture. So suppose R is just algebra with identity, okay? And I have a linear map of R to the M to R to the M as right vector spaces. So I may consider them as left vector spaces or right. Well, just let's choose that they are right vector spaces. Now, again, this is classical definition that a vector V is called a cyclic vector, a capital and cyclic, actually this is cyclic vector, if this is the m vectors that are written here, V, then you apply AV, then you apply A square V, so on to V. And if you have a basis in R to the m, then it's called a cyclic vector just for this linear map. Okay, but then if you add another power of a to the m, then you must have a linear relation between some linear combination of these vectors must be equal to 0, because you have m plus 1 vectors in m-dimensional space. Okay, I will denote those coefficients by lambda I, depending on v and a, and there are m such coefficients. Okay, so here they are written, and so I assume that the coefficients for a to the m of v is 1. Well, so actually, what you have here is actually Cayley version of non-commutative version of Cayley-Hamilton theory. And then, as a commutative case, you call this is the coefficient for the free for v. You call it determinant. Determinant depends on vector v. And so the first coefficient, so lambda 1, you call the trace of v. We will see some examples later. But so if R is commutative, then this lambda m is determinant of A, and lambda 1 is the trace, and they do not depend on your cyclic vector. Any cyclic vector will give you the same result. In the non-commutative case, the situation is not so. It depends on, so those expressions, lambda I, so those coefficients then depend on vector v. But they provide some information about A. For example, if this determinant, which is, of course, lambda m VA, this m is omitted. I should put m here, is 0. Then the map A is not invertible. Okay, well, classical case, if determinant is 0, then matrix is not invertible. Now I compute those, so those coefficients, for example, the determinant. Well, in the case when v is just a coordinate vector. So for simplicity, I took E1, so which is 1, 0, 0, 0, 0. But you can take E sub I when 1 is on the ith place. And now, new notation, if I consider the power of A to the k, and I treat A as a matrix, then on Aij, this is k, is the entry of A to the k of the index ij. Okay, then you may write expressions. So I will write expressions for determinants only, and you see this expression. So this is sort of Vandermonde-like expressions, because so just in each row you have entries of different powers of this matrix A, but I can compute this as a determinant. Now, just to convince this that it looks like determinant, I consider the simplest case, and I take m equals 2. Well, again, v is just this coordinate vector e1. Okay, and then I can compute the trace, non-commutative trace, but then there will be many non-commutative traces. And you see the formula, which of course in the commutative case is A11 plus A22, but in the non-commutative, again, you have this category property that if ARJ is a morphism, that they all have to start and to end in the same space. So here I have A22 conjugated by A12. So if I have morphism, I go from 1 to 2, from 2 to 2, and this inverse from 2 to 1. So this is it. And you see an expression for non-commutative determinants. Again, in the commutative case, you have A11, A22 minus A12, A21. But in the non-commutative case, so A12 and A21, they are composable. A22, A11, they are non-composable, but if you have this conjugation, everything is composable. And one can do a lot of such computations. And now, let me just note that when A is a quantum matrix, and commutative, then these determinants of this dependent of coordinate vectors for every I, they are basically this determinant of this quantum determinant of A multiplied by power of Q, but Q is just a constant. So I can leave it as an exercise. Next application, this is related to quasi-determinants and to characteristic functions of graphs. So let me consider just a matrix with the entries Aij, and I consider them as free variables. Okay, then what I will do is the following. If I want to consider quasi-determinant Aij, then I will remove from A a row of index I, a column of index J, and then in the remaining matrix, I will choose exactly one element in I will choose elements, actually n minus 1 elements, such that in any row there is exactly one element, and in any column is exactly one element. For example, if I and j are equals to 1, then I can take A22, A33, and so on, A and N, going just along the diagonal. Okay, this is what's actually saying here. This is my choice of indices PQ. And when I choose such elements, it means that in my formulas, these elements will be always invertible, but no other element will be invertible. Okay, this is just explanation of what's going on. Okay, and then I just leave again my elements outside of this set of indices J as before, so AKL, and four elements for indices from this J, so I have just inverses. Well, again, just an example would be that I equals 1, J equals 1, and then the rest of diagonal elements is. Okay, so if I just define this, okay, then I will consider just this some formal series. Let me recall that these are free variables. So then I consider this formal series. But again, this monomial is composable. So I go from I to I1, from I1 to I2, then eventually I go to IS, and from IS I go to G. So all these monomials, they correspond to some sort of paths from I to J. And so the sum is taken here over all sequences on the condition that the synthesis I1 so Ik, they are not equal to Ij. I can write you the inverse formula for these quasi-determinants, but in this case I allow there's no condition on this sequence A1, I1, and so on. Now, and basically, I can use this actually formal series as a definition of quasi-determinants and can deduce all formulas just from this formal series. But what is interesting that the above formal series can be interpreted in terms of graph. So I have a complete oriented graph with vertices 1, n, and edges EKL, which means this is the edge from vertex number K to vertex number L. Again, it's oriented. Now, there is a bijective correspondence between the edges of the graph and the elements BKL. So this is just a correspondence. And then when I have this monomial, and this is monomial just from this sum, then this monomial corresponds to a path from vertex I to vertex J. So I have just a bijective correspondence between monomials and the paths, and my formal series means that I have to travel from I to J in all possible ways, and then sort of to consider just a linear combination of these paths. Okay, again, let me emphasize that the monomial consists of sort of composable elements, and basically such construction is somehow related to automata theory. And Okay, this is just so this is how graphs help you to understand quasi-determinants. And I believe I talked about my first lecture that you can write actually this formal series of quasi-determinants. Okay, and I'm also, since I'm talking about again quasi-determinants, I would like to use quasi-determinants to define so-called non-commutative Catalan numbers. So let me recall what are Catalan numbers. Well, they are very popular in combinatorics. They can be compared only with binomial coefficients. And there are at least there are several hundreds equivalent definitions of Catalan numbers. So this, if you want just to use just formulas, here is the formula. So you consider this binomial coefficient 2n choose n, and you divide this by n plus 1. Okay. Now, very popular recursion is that Cn plus 1, which is a very Catalan number, can be written as the following sum. Okay, and to have this recursion, you have to check that, or you have just to put C0 and C1 equals 1. And actually, this recursion can be expressed by using a generating series. So then there is a quadratic formula for connecting, actually generating series for Catalan numbers. But basically, if you know this recursion, it's easy to write this formula. Okay, now there is a less known definition of Catalan numbers. And it's the following, that suppose you solve this equation, this determinantal equation. So you have this your Hankel matrix of Catalan numbers, you can see it, but you start with the C0 and C1. And if you demand that such determinants equals to 1, then you can find solutions, and solutions will be exactly these Catalan numbers, which I defined before. And they satisfy this recursion, so everything is. And okay, and then we decided the following. Okay, what if we have not determinants, but quasi-determinants, and we start with the right low corner, what exactly this place, and take this quasi-determinants. Now, again, in the classical case, you will get 1 as well. Okay, but now we don't want 1. We introduce an infinite sequence of formal variables. So they do not commute, they are free letters. Well, starting with a 0, so you have x0, x1, x2, and so on. And you define these non-commutative Catalan numbers as solutions of this quasi-determinant equation. And so I will use capital letters for my Catalan numbers. And here you have just this quasi-determinant equals 1. And I want to solve this for this sequence of quasi-determinants. Now, the solutions are surprisingly rather simple. They are not rational functions, but the quasi-determinant is actually a rational function. But in this case, the solutions are Laurent polynomials. So let me just write this. So C naught is X naught, C1 is X1, C2 is X2 plus X1, X naught minus 1, X1. And so C3 contains 5 terms, which are, well, you can see X3 plus X2, X1 minus 1, X2, X2, X naught minus 1, X1, X1, X naught minus 1, X2, and this one. Okay, I will, and so on. I could write you C4, but it will contain 14 terms. Okay, so what one can notice? So first of all, that positive and negative powers, they are just going one after another. So you have just a power 1, power negative 1, power 1. Power 1, power negative 1, power 1, power negative 1. So just these powers alternate. Also that the number of these monomials is exactly the name, they're equal, this just classical Catalan numbers. So C2 is 2, C3 is 5, and you have here sum of 2 terms, here you have some 5 terms. Also, what is interesting that if you will read those monomials from the right, you have exactly the same expression. So that's here, so just this. So this some monomials are just symmetric, but for example, for C3, you have x2, x0 minus 1, x1, and x1, x0 minus 1, x2. If you read those monomials from the right, they will just interchange. Okay. So what do we have? Let's use some algebra. So you have a free group generated by x0, x1, x2, and so on. You may consider subgroup which generates only the x's up to xn. Now, and non-commutative Catalan number Cn is an element of the group ring. Well, actually, this must be a ZFN. And now, since you have just a free group, so you have elements are words. Words you can read from left to right or from right to left. It's basically so it has an anti-involution, and all Catalan numbers will be will not change after this canonical anti-involution. Then I can write a recursion, a recursive relation that generalizing things that I have in the commutative case. Here they are. And let's try to do this. in the non-commutative setting. Okay, first of all, but here I need an endomorphism of this group ring, and this is just a shift of the number. So t applied to xk is equal to x plus 1, and then you can extend for all monomials using morphism. And then I have this, so c n plus 1 equal just this sum, which is equal, so this is ck x naught inverse t k. And here, this is just a similar result. So just this one. Well, again, let me emphasize that if I will consider if I will just use equation for each x, xi equals 1, then I will specialize this formula to the classical form of this. Okay, now there is a classical Catalan numbers have combinatorial description, and I would like to sort of discuss now combinatorial description for non-commutative Catalan. Okay, so suppose I have just a lattice with so this I have a plane with coordinate planes, and the lattice is just points with integer coordinates, and I consider so-called monotonic passes from passes in so in this square, so this from this just in this square. So I will correct some later. In this square, I have square of the length n, and I can see the passes from just 0 point to this, so this, well, to the point with coordinate n. And those passes goes like this. I move to the left by 1. I can move to horizontally to the left. I can move vertically. I can move vertically, but I never can actually cross the diagonal connecting this 0, 0, point 0, 0, and point n. I can touch it, but I cannot cross it. And now then, well, let me just say it's more formally, so that the P is a Catalan, the path P is Catalan, if for each point this. So this was with coordinates P1 and P2. So the so P1 is greater or equal than P2. Now the difference I will denote by C of P, because in the literature it's called content. Okay, now it is known then the number of such passes. So again, this condition in this square is exactly this classical Catalan number C. Okay, now let me do some non-commutative flavor. And to associate a monomial in axis, actually Laurent monomial in axis, to this path P. And so if you go just from 0, 0 to Nn, so, and your paths have angles. You go horizontally, then up, then horizontally, then up, and so on until you arrive. And in each turn, you have an angle. I will classify those angles. So one, the southeast angles, southeast corners. And when I go horizontally and then up, and then northwest corners when you go up and then horizontally to the right. Formally, this is explained. What is written exactly explains this situation. And then to this path, I'm assigned an element in this group fan. So, and this is just a product. So I go from left to right. I'm finding corners. So this the content. This is just a non-negative integer, which give me just sort of this the number of this x of this free variable, and depending on the structure of this corner, I will assign to each power 1 if the corner is southeast, again goes to the right top, and -1, and it is northwest. So if it goes up and to the right. And so then I have monomials. And then my C sub n is just the sum of these monomials, and the sum is taken over all passes from all Catalan passes from just from the left upper, from the left low corner of my square to the right upper corner of my square. And the same, you can have this homomorphism when xk goes to 1, and then the image of this Catalan number is the ordinary number. Okay, so then let me maybe clarify a little bit so what I said. So let's look at these examples. So, well, so C naught, X naught, I cannot move, just I have just one point, put X naught. X1, it means that I have just a square of the size 1. So I go to the left and up. And so I have exactly southeast corner. The content is 1 minus 0 is 1. So I have x1. Now, if I have 2 by 2 square, then how I can go from low left corner to upper right corner? I can go from 0 to 2 and up immediately. Okay, again, the corner is southeast. The content is 2, because 2 minus 0 is 2, so I have x2. Now, and I have one more pass, and this means that I will move from by step 1 to the right horizontally, then by step 1 up, and I reach diagonal, and then one step to the right and one step up. So I have actually 3 corners. One is when I go just by step 1 according to this x-axis. So this it's and then up. So then the content is 1 minus 0 is 1. It's southeast, so the power is 1. Here then I go up, and I'm on the diagonal. On the diagonal, so P1 equals P2. So the difference is 0. I must have 0. But I have just this sort of the turn like this, up, up and to the right. So this is actually northwest corner, so I must put -1. And now this one, I go from the coordinate 1, 1 to coordinate 2, 1. So the content is 2 minus 1 is 1. And the corner is northwest, so I have just 1 here. So here I got this one on. I can do the same for each of these 3, but I'm afraid that it will be a little bit. So this is actually the theory of non-commutative determinant. You may construct the theory of non-commutative binomial coefficients and so on, but I will not go into these details. It's written actually in our paper. Okay, now it's almost time, and I would just mention some other papers which are related to this talk. Okay, and one paper, this is joined with Arkady Bernstein. It's called Generalized Joint Action. So let me explain that when you have just variable y and a variable x, that in the commutative case, then you can just consider this conjugation, e to the x, y, e to the minus x. And then you can do the same in the non-commutative case and basically try to write what you have. Basically, you will have just expressions with a lot of commutators. But you can do this in more general. So instead of these exponents, you may consider any power series which starts with non-commutative coefficients, which starts with 1, because you want them to be invertible, and to use this and consider conjugations with this action. So this is just in this paper. Now another relations with the Catalan numbers is actually this problem. So suppose you have this series depending of non-commuting letters A and B, A and Bn, and you want to write this reciprocal in a good way. And surprisingly, you have then appear another type of non-commutative Catalan numbers. And basically, everything is related with the solution of non-commutative quadratic equations. So this is just, so this is rather short note, but it has like 4 authors for this one. And since somebody asked me about this non-commutative groups, classical groups like SLN and so on, I could mention again our joint paper with Arkady, where we considered sort of Lie algebra, trying to build a theory of Lie algebras and Lie groups over non-commutative rings. So I will give all references in archive, but it's published in some journals, so I can give references in journals if needed. And so probably I will stop here. So just to what I'm trying to do, that when you're playing with pure non-commutative variables, so some people believe that nothing interesting will happen, but I don't think so. I try to convince you otherwise. And I will stop now. So thank you again very much for the invitation.
Okay, so thank you very much for wonderful lectures.
Mm-hmm.